Hello, everyone. Welcome to our seminar. Today, we are very happy to have Nicolas Curie, and he will talk about scaling limit of planar maps with large faces. Thanks, Nicolas.
Thanks a lot for the invitation. It's a pleasure to speak at this seminar in front of this very impressive audience. So here it goes. So scaling limits of planar maps with large faces. So it's a work that we've been completing with Grégory, Miermont, and Armand Riera for 2 years now. And let's hope this is the final year and it will be an archive before the end of this year. Fingers crossed. Okay. So, maybe I don't need, but anyway, so let me recap the standard planar map result about triangulations. You have a bunch of triangles that you glue in a uniform manner to get a sphere, a topological sphere. So there are finite number of ways of doing that, and you pick one uniformly at random. You distinguish one oriented edge to keep the symmetry, and this is a random triangulation. You see that as a metric space because it's a graph, and you endow it with the graph distance. And here are a couple of simulations of very large random triangulations which are embedded in the three-dimensional space in a way which is as close as possible to an isometric embedding. It is not an isometric embedding, but it gives the flavor of what would be an isometric embedding. So that's the rocking horse. It's a bit on the side. The goat with an umbrella. Here is the umbrella, as you can see. The executioner, or some people like to call this one the beheaded chicken. Période bleue à la Picasso, and period rose, pink period, still with Picasso. Okay, so these are samples of random triangulation with a couple of thousand triangles. And the landmark is the theorem of Jean-François, Le Gall, that you can see here, that if you pick a triangulation of the sphere with n triangles uniformly at random, then when n is large, you see that as a metric space, the vertex set of this triangulation. You equip with the graph distance, which you renormalize by n to the -1/4. Then you've got convergence for the Gromov-Hausdorff of topology towards this guy, which we call the Brownian sphere. So this guy is a random compact metric space whose Hausdorff dimension is almost surely 4, but still almost surely homomorphic to the two-dimensional sphere. So the topological dimension is 2 and the fractal dimension is 4. So this is a theorem of Jean-François and Frédéric Paulin back to 2006. And so this guy, the Brownian sphere, has been studied a lot. It is universal in the sense that it can be obtained by taking scaling limit of other classes of planar maps. For example, quadrangulation, as Grégory showed in the same time as Jean-François when they proved this theorem. And of particular interest is the study of geodesics in this random metric space. And so the behavior of the geodesics has been studied a lot as well. And finally, this space, the Brownian sphere, has been shown by Miller and Sheffield to appear directly in the Gaussian free field. If you normalize the exponential of the Gaussian free field properly, you can define a metric on the sphere, which, seen as a random metric space, is the Brownian sphere. Okay, I guess you all guys are familiar with this work. But the goal of today is to get to the stable paradigm. So this paradigm can be thought of as the Brownian paradigm, when all the faces are small, you know, triangles or quadrangles, they are small faces. And we want to see what appears when you have large faces. And so let me make the parallel between different kind of random objects. For processes, when you have random walk with small steps, increments, which are centered and say finite variance, then in the large scale limit, you see Brownian motion. But if your increments can be large, we will have a polynomial tail with no variance, then in the limit, you see those stable Levy process. So that's on the level of process, and this is well known, goes back to Wiener for Brownian motion, Levy for stable process. Same phenomenon appears in the realm of trees. When you have random trees with small degrees, let's say binary trees, then the scaling limit is given by the Brownian tree of Aldous. But when you have large degree vertices, those hubs that you see there, then the scaling limit is something different that has been introduced by Le Gall and Lejean in 98. Okay, so we want to do the same with maps. So when you have small degree, the scaling limit is universal to some extent, and is the Brownian sphere. And the goal of today is to look for this case of stable sphere or stable maps. Okay, so to define properly the model, let's go back with this gluing of polygons, but instead of gluing triangles, you will glue a sequence of polygons so that the total perimeter, the sum of all the perimeters of your polygon is 2n. So you got n edges after the gluing. You still glue them in a planar fashion so that you get a topological sphere in the end. And it has been shown in a very general setup by Cyril Marzouk in the bipartite setup. So when all the degrees are even, that provided that the faces, the polygons have small degrees, then the universal scaling limit is the Brownian sphere. But now we want to force large faces. And to be more precise, we want that the number of faces within this degree sequence, the number of faces of degree k, 2k, because I will focus on the bipartite case soon, is in proportion decaying polynomially like k to the minus a minus 1, when a is a number between 1 and 2. Okay, so you have still a few faces which have a polynomial degree. Okay, and we want to know how does it look like. So here are a few simulations. So let me just recap, keep that in mind. This parameter A governs how many faces with large degrees you will have. If A is close to 2 or even larger than 2, then you have few faces with large degrees. But if A is close to 1, then you may have many faces with large degrees. So the smaller A is, the larger the faces you will see in the scaling limit. Okay? So when A is close to 2, when you do simulations, you see stuff which are very reminiscent of the Brownian sphere. Well, this is looking like the goat with an umbrella, except for a few faces which are very large. When you diminish A, large faces appear, and they tend to be more and more present as A decreases in the scaling limit. And suddenly something will appear around A, which is 3/2. You see that faces, they are all over the places. And even if you go below 3/2, then the simulation are not that nice because it's hard to display the faces when they are really intertwined in the map. And so it's a problem of how I drew the simulation in a 3 space, not the faces themselves. Okay. And if you keep going down, then you have faces all over the places. You can also do the dual of those maps. So instead of gluing large degree faces, you take the dual, and in the dual version, you will have large degree vertices. And here the simulations are due to Timothy, but we start again from A is equal close to 2, which is the Brownian sphere case, where we see almost a Brownian sphere with a few hubs, with a few large degree vertices. As you decrease A, those large degree vertices, they tend to be more and more present until A is equal to 3/2, where they are really present. And after that, you even have some very dramatic phenomenon, apparition of a tree-like structure, if you wish, in the map, where those very large degree vertices, they tend to shorten the distance a lot. Okay? So here is a little recap of what we know. So what do we have? We have the parameter A that varies from 1 to 2 here. Above 2, it will be the Brownian paradigm. So when you have small faces, here you have large faces. What you will see, what you will see on the left-hand side will be for the map with large faces. And what you will see on the right will be for maps with large degree vertices, so the dual. Okay, so what is expected is when A is above 2, expected, I say, that both the map and the dual should converge to the Brownian sphere. So it is known in a few cases for triangulations. For example, for triangulation, we know that both the map and its dual converge to the Brownian sphere, but it's not known in the full generality, but it's believed to be true. And the diameter, as I mentioned, is of order n to the 1/4. Now, if you have this parameter A, which is below 2, between 1 and 2, then Legal and Miermont proved in 2010 that at least the good order for the diameter of those beasts with large faces is n to the 1/2a. So it matched with 1/4 when a is equal to 2. Okay, but they did not prove any scaling limit result. They have a tightness result. We will come back to that, but they did not identify the limit. More recently, with Timothy on the dual side, so with large degree vertices, we proved 10 years ago, roughly, that the diameter of those maps with large degree vertices should be of order n to the a minus 3/2 over a. And you see there that when a is equal to 3/2, this is 0. So the exponent is 0. And actually, we proved so in an infinite model, not in the finite model, but it should not be that complicated to prove that for finite maps, that the diameter of those maps in this regime, when a is below 3/2, should be logarithmic in n. So really a crumpled phase. Also, with Timothy and Cyril, we studied the case of this critical case when a is 3/2, a special case actually, where the diameter should be of this strange logarithm squared. Okay, so no scaling limit is expected in those regimes there. We expect a scaling limit here, but I will not talk about that in this work. And this work here, this seminar is focused on this case of establishing the scaling limit for maps with large degree faces in this regime. So completing the results of Legal and Miermont. Questions about this tabular? No?
There's a question here. Nicolas?
Yep.
There's a question from Armand.
Yeah, so as A tends to 3/2, how does the transition happen from power to log? Do you know? Like if you make equal to 3/2 plus.
If you want to scale A with n, a near critical limit?
Yes, yes.
I have not tried. Interesting question. No, I have not tried.
But on a heuristic level, do you know?
I should do a back of the envelope calculation, not on the spot like that. No, I don't know how the constant in front of this power should blow up as A goes to 3/2. Good question.
Thank you.
Okay. All right. So same recap. The scaling limit should be for the dual, the primal and the dual map should be the Brownian sphere. As I announced today, we will talk about stable maps here. And scaling limit here should be the stable spheres if they exist. And here, no scaling limits. And we will see a dichotomy. We will see a transition at A is equal to 3/2. We will see that the topology of the scaling limit here and there are different. Okay. An additional motivation to consider this model of gluing faces with large degree comes from the statistical physics, from the ON model. And so what is believed is that when you have an ON model, you can consider it gasket. So the gasket is you have a point and you remove all the loops except the outermost ones. And if you play this game for a critical statistical physics model, so this ON model coupled with a map, so the map is biased by the partition function of this statistical physics model, and you play this game of taking the gasket, then the gasket of the map should be one of these stable map, and the exponent A is related to the n of the ON model and to the kappa of the describing SLE by this relation. Okay, and we prove that to some extent with Loïc Richier and other collaborators for critical percolation on planar maps. We know that if you do critical percolation on planar maps and consider the gasket, then it is a stable map with this parameter A is equal to 7/6. Okay. Now, let me describe the exact model, because I said we have a gluing of polygons. So this is the prescribed degree setup. Actually, we want some randomness in the size of the polygons we want to glue. And to do that properly, I need to define the Boltzmann measure on planar maps. So planar map, a graph drawn on the sphere or gluing of polygons. And in this talk, from now on, I will focus on the bipartite case where all the faces have even degrees. Maps are rooted, and a map is given by something like that, gluing of polygons, and the weight. So I will have a measure, a probability measure on this. Before that, I will have a measure, and the measure of this guy is just a product measure. So the weight of a map M is the product of all the faces of some weight Q indexed by the degree of the face, divided by 2 because it's even. And this Q is, roughly speaking, a polynomial that decays like k to the minus a minus half. The a is the same as before. A is between 1 and 2. Okay? I put under the rug the fact that this sequence has to be fine-tuned. Okay, this is, let me go quickly over that. You have conditions to get a critical model, and the critical model can be turned, you have sequence for which it is critical, and I mean that the expected size of a map squared is infinite. It's like the Galton-Watson measure for those who know. You have a Galton-Watson measure. If you want it to be critical, it's requiring that the size of your tree has no first moment. Here, it's no second moment. Okay? So once you have this measure on your map, you want to study large maps. And so you take this measure and you condition on having size n. Size could be the number of vertices, faces, or edges. It doesn't matter. And you want to study the geometry of this object. And just to remember, roughly speaking, the number of faces of perimeter or degree k has a proportion which is k to the minus a minus 1. Okay. So here is the theorem. We are completing the results of Grégory and Jean-François, and we prove convergence of those maps seen as metric space, as usual, rescaled by the factor which has been discovered by Jean-François and Grégory, the order of magnitude of the diameter, which is n to the minus 1 over, okay, the diameter is n to the 1 over 2a. And we have a scaling limit here. So what is this guy? SA. SA is what we call a stable carpet or gasket. So it's a random compact metric space. It has a metric, the metric which I will call D star. There is a renormalization factor CQ, which depends on the particular weight sequence, but forget about that. And so this space, as I said, is a random compact metric space. of Hausdorff dimension, which is 2A, almost surely. And furthermore, the topology of this guy depends on the parameter A. If A is above 3/2, then it has the topology of a Sierpinski carpet in the sense that the holes or the faces, we will come back to that in a minute, do not touch each other. And if A is below 3/2, then the faces of the map touch themselves and each other in the scaling limit. And the topology is different. We believe that the topology is an almost sure topology, but we have not characterized it yet. Okay, to be fair, Jean-François and Grégory, so 12 years ago, proved this convergence along subsequences. Or in other words, they proved tightness of these random variables in the Gromov-Hausdorff sense. So what remained to be proved is the uniqueness of the scaling limit. So it's exactly where we were for the Brownian sphere in 2005, before the breakthrough of Jean-François and Grégory 5 or 6 years after. Okay, so just a picture to illustrate this dichotomy for the topology. So when A is above 3/2, 3/2 can be included actually. We are in what the physicists call the dilute phase, and the metric space has holes. We will define those holes in a minute. But these holes, they have a boundary which are made of simple cycles which are not intersecting. And when A is below 3/2, we have holes, but the boundary of these holes, they can touch each other and themselves. And so you have a much more complicated fractal structure, and the topology is much more complicated. So the topology of the guy on the left is universal. It is called the Sierpinski carpet. It's a topology of anything, any compact that you could draw on the sphere, so that the complement of this compact is made of connected components, Ci, so that you can enumerate those components and their diameter goes to 0. And the boundaries of those holes, they are simple closed curves which do not intersect. And those holes have to be dense. So this is the Sierpinski carpet. On the contrary, on the right-hand side, you have a gasket where the holes can touch each other. Okay, so of course, I should mention, or let's skip that the dimension of the faces is always 2, but skip that. Of course, this dichotomy is the same as the dichotomy for SLE, which is touching itself above kappa is equal to 6 and simple curve below. And it's the same transition if you believe in the formula that is written here, that A is half plus kappa over 4 over kappa. Okay, questions? Okay, if not, let me move forward. Let me describe a little bit the behavior of the geodesics in those spaces. So those spaces, they are compact, abstract, compact metric space, but actually they can be, you can really see that as, you can embed them non-canonically, but you can embed them on the sphere and think of it as a random metric on the sphere with holes. And so if you pick 2 points, you can ask what does a geodesic between those 2 points in your metric space, what does it look like? So the metric space here is in gray, and what you see with colors are the holes, the complement of this metric space. And you may think that a geodesic will try to avoid the void of this space and try to, you know, get in between. Actually not. In the full regime, what did I wrote? In the full regime, when A is between 1 and 2, in the full regime, the geodesics, they will touch the faces. Actually, they will bounce on the faces back and forth to get to this point to the other one. And this will be very useful when doing the final step of the proof, if I can. Okay, so that's for the knowledgeable readers or listeners. Here I'm drawing the parallel with the proof of the uniqueness of the Brownian sphere. And roughly speaking, the strategy is the same, but at key places, we have to play differently. So how does it go? So the starting point is the same. We will use bijections, those Schaeffer, Bouttier-Di Francesco-Guitter, and so on bijection to encode our maps with label trees. That's the starting point. This has been done. It's already in the work of Jean-François and Grégory 10 years ago. Then we want to take this encoding and pass it to the limit to get, so in the case of the Brownian sphere, you get this Aldous CRT and the Brownian snake. We want to do the analog of this. This has been done by Jean-François and Grégory and others. Then you have this analog of the Brownian snake, which is the label process on the tree. We will see that in our case, it's not a tree anymore, it's a loop tree, but you also have a process on this guy, which we will call the label process. And we want to study this label process because the fine property of this process will be very helpful when proving the convergence. And this is very different. Why? Because in the Brownian sphere case, we had the tree, we had Aldous CRT, and we had the Brownian snake on it. And this has been studied by many people, Le Gall, Perkins, the connection with the differential equations and so on. Many people, Dinkin, of course. So many people studied that. So there were many tools to study the Brownian snake. In our case, nobody. And so the connection with partial differential equation is lost and so on. So we have to play differently. Okay, now we want to use this construction, well, this discrete construction to build geodesics towards a distinguished point and create a putative metric, D star. This is the same as for the Brownian sphere. In a nutshell, we can create paths that we know are geodesics towards a point, but then towards a distinguished point. But then if you want to get geodesic between 2 points which are not the distinguished point, then you need to, go back and forth between those geodesics to the root, and this creates for you paths, but you are not sure that there are paths which are much shorter than those ones. So you create a putative metric D star. And the first thing you want to show is that this D star defines the good topology, that it actually identifies the good point. This is the analog of the Invenciones paper of Le Gall 2007. And here I claim that in our setup, this part is easier because we have faces, and you'll see that faces are really helpful. Then we will identify the topology in the dilute phase. As I said, it's the Sierpinski carpet. And this uses the same argument, the same topological argument. Okay. Now we are at the level of 2008 for the Brownian sphere. And now we want to prove uniqueness of the Brownian sphere. So now we want to prove uniqueness of those guys. And there, the idea is the same, is to start from a typical geodesic, and you want to get a description of the typical scenario along geodesics. And there were two roads that were different, taken by Le Gall and by Miermont. And we take actually a third road, which is a bit in between. And this is harder in our context because the objects are a bit harder. Now we want to use this description of geodesic to do surgery along typical geodesics and replace pieces of typical geodesics by pieces of geodesics towards the distinguished point. And this is really different we are using new ideas there, which are really different. And above all, we need a priori bound on the distance to control the effect of this surgery. And this also is very different from what has been done in the Brownian sphere setup. And we think that this is more robust. Okay, so let's start with item 1. If you have questions, please ask. Which part do you want to see, or which part you don't want to see? If you have preferences, please tell me. Otherwise, I just go forward. Okay, so step 1 is encoding of the map with label trees. Okay, for you, if I go on the list, I guess you all saw that at one point in your life. It's the Bouttier-Di Francesco encoding of bipartite maps. So what you have on the left is mobile. Mobile is a plane tree with vertices of two types, black and white. They alternate. The white vertices, they have labels. The labels are just integers. The black, they don't have labels. And the condition is when you go around a black vertex in clockwise order, then the labels can increase by any quantity, but they cannot decrease by more than 1. Okay? Here you can decrease by 1, you can decrease by 1, you can decrease by 1, you can increase, but then you can decrease only by 1. Okay, and we will usually represent this tree via its loop tree. So the loop tree is just obtained by replacing every black vertex here with the cycle of all the white vertices around and connecting them, as you can see on the picture. Okay, and now from those objects, we apply the Schaeffer rule and create a map. So what is the Schaeffer rule? Let me remind you that you imagine that you do the contour of the tree, you go around the tree or around the loop tree, it's the same. And each time you encounter a vertex with label I, so a white vertex with label I, you connect to the next vertex in the contour order with label I minus 1. So this 0 is connected to the next minus 1, which is this one. And you move forward, you go to this 4, you connect to the 3, you move forward, 3 to the next 2, 2 to the next 1, 4. It's the same 4, but you come from another corner, so you still link it to another vertex. 3 to the next 2, 2 to the next 1, and so on and so forth. Okay? When you arrive at this vertex minus 2, it's the vertex of minimal label in your tree, and so you cannot connect to the next minus 3 because there are no minus 3 in your tree. So you put just one vertex on the side with label minus 3 and you connect to it. Okay? And if you do that for the whole contour, you get a map. Sorry. Oh. Sorry. If you do that for the whole contour, you get a map. And what is nice is that you see on this picture that the faces of your map, they are exactly the black dots here. So the faces of your map corresponds to the vertices, to the black vertices of your tree, and the degrees of your faces is just the degree of your vertices multiplied by 2. So here you have a large degree faces, here a face of degree 4, here a face of degree 2, here a face of degree 8, and so on and so forth. So remember that the faces will correspond to the black dots, and the black dots will correspond to the loops here in the loop tree. And so the size of a loop will be the size or the perimeter of the faces in the corresponding map. Okay? And remember that the label process in a given face here is just, if you shift it by an additive constant, is just a random walk that can do positive jumps, but negative jumps of at most 1. But if you really think about that, actually, you don't want to make a very big positive jumps, because if you do a very big positive jumps, then you're forced after that to do all -1, -1, -1 to come back to your starting point, because you're in a loop. And so actually, you will see that you have when you go around here, you will, in the scaling unit, you will not see big jumps in the label process, that the label process will vary like a random walk. Okay, so formally, you have this tree, this label tree, which is encoded by 2 processes. The first process, Sn, is the usual Lukasiewicz exploration of your tree, and which is in black here. And the red process is the label process, which records the labels of your vertices when you explore this tree in the contour. And Legan and Miermont already proved the convergence of those processes. You need to renormalize the Lukasiewicz process by n to the -1/a, and the Lukasiewicz path by n to the -1/2a. They converge towards a pair of process. And the first one is just an excursion of an alpha stable Levy process with only positive jumps. This is very standard because it's just the Lukasiewicz path of a tree. Okay, it's a bicolored tree, but actually it's not a big deal. And this tree, we did everything so that it is critical, and that the orthopic distribution of the black vertices has a heavy tail in the domain of attraction of alpha R-stable law. So this, we did everything to be in this setup. And the label process is a process which is coupled with this one. Okay, to describe it, it's actually kind of simple because this excursion, so this limit of the Lukasiewicz walk, this excursion of the alpha R-stable Levy process encodes what is the scaling limit of this discrete loop tree, and that we introduced with Igor a couple of years ago, which is the so-called stable loop tree. So the stable loop tree is just, you imagine you take the scaling limit of this object and you renormalize the loops by n to the -1/a. So what it is a random compact metric space of dimension A, which is obtained by gluing loops together along a tree structure. But beware, if you look at 2 big loops, they are not adjacent. They are not glued to each other. It's like in the rational, between 2 rational, you've got infinitely many rational. Here also, between 2 loops, you have infinitely many small loops. Okay? And the label process, well, almost by definition, the label process is the scaling limit of what you get in the discrete, and it should be the Brownian motion indexed by this loop tree. Or if you prefer, the Gaussian free field indexed by this loop tree. The loop tree is given, this is this random structure, and now you want a process that is indexed, sorry, by the loop tree, and which along every loop moves as a Brownian motion. So formally, what you do is for every loop of your loop tree, you sample a Brownian bridge of the corresponding length. This gives you the variation of your labels along a loop, and then you glue that together along the loop tree structure. So you have to be a bit careful, of course, because you glue infinitely many loops and so on, but you can do that. Okay? And so in the process version, every jump of your stable process, every jump here in orange will come with a Brownian bridge, this BI. And if you want the label of this point T, then you add the increment of all these Brownian bridges when you go back in the ancestral line from T to, let's say, 0 here. And so this label process, this Gaussian free field on the loop tree, is well defined and is half Hölder in the metric of the loop tree. So it's really the Brownian motion indexed by the loop tree. And half of the paper is devoted to study this process, and more precisely, to study the records, the minimal records of this process. What are minimal records? Well, you have your process, which is indexed by 0, 1, and you look at when does this process reach new minimum. Why? Because if you remember a little bit, in the Schaeffer or Bouttier-Di Francesco-Guitter construction, when you connect 2 points, you look for the next -1 or the next -2. And so if you iterate this construction, you will surf on the minimal record of your label process. So this is of the greatest importance. And actually, local minimal record, we prove that they never appear on pinch point. What are pinch points? Pinch points are points in between loops, let's say. So they never appear there, but they can appear on the loops. And actually, the dichotomy for the topology comes from there. You may have records which are two-sided records, if only if, two-sided meaning it's a record from the left and from the right, if only if you are in the dense phase, A is strictly less than 3/2. But you always have one-sided record on the loops, and this will give you the fact that the geodesics touch the phases in the whole regime. Okay, so let me give you one ingredient that is geometrically very different from the Brownian sphere. It's the improved Cactus bound. So imagine that I have for you a map, a discrete map, which I display as a cactus by picking one point, putting it down, and then putting all other points at a height which corresponds to the distance to this distinguished point. This creates for you a cactus representation of the map. So this is really a two-dimensional object. And it is easy to see that this Schaeffer or Bouttier-Di Francesco-Guitter encoding, they describe very well for you the geometry of this cactus. In particular, if you have 2 points, blue and red, and you want to ask, are they identified in the map? Do they correspond to the same point? Well, there is a very easy case, is if the blue and the red do not have the same distance to the root, they cannot be identified. That's trivial. So this you can read very easily in the Schaeffer encoding. Another easy case is when you have 2 points, blue and red, which are at the same height, so the same distance to the root. They might be identified. Not if there is a path here, which has a height which is lower than the height of the blue and the red. Because you know, if you know the cactus, you know that if you want to go from the blue to the red, then you have to go down before going up. You cannot go from blue to red, and staying at the same height. Okay, so you can distinguish those 2 points. But the annoying case in the Brownian sphere case, and which is the core of the Invenciones paper of Le Gall 2007, is to distinguish 2 points that the cactus does not distinguish. So 2 points, blue and red here, which are at the same height and which are not separated by a path. Then in the Brownian sphere, there is this very nice argument of Le Gall based on the volume considerations. But in our case, we claim that in such a situation, there will be a face separating those 2 points. So actually, when 2 points are different in the map, there will be a face separating those 2 points, meaning that if you want to go from blue to red, this face crosses the height of the blue and red, meaning that every path going from blue to red must go at a height which is a bit higher or must go at a height which is a bit lower. Of course, you should have another face on the other side of the map so that you don't have a path that stays on the same level and go on the other side. Okay, so their faces help a lot distinguishing points. And this is the translation of what I just said. This existence of faces is described in terms of process by this improved Cactus bound. So let me go through that slowly. So imagine you have a point here, S, and a point here, T. You see the loop tree here. So imagine that this is really discrete. You have your loop tree, discrete loop tree, and you have labels all over the place, and you build all this red path in the Schaeffer construction, which will form for you the map. And you ask, okay, are those 2 points close in the map? Will they correspond to the same point in the scaling limit? Okay. Now imagine the following scenario. Imagine that you have a point. Okay, imagine that the label of this one is 100 and the label of this one is 100 as well. Same label, so the same distance to the root. But imagine that here you have a point which is, I don't know, 50 and 50 also here. So if you start from the 50 and you iterate this successor in the geodesic construction, you will go 50, 49, 48, and so on, until this guy, call it 0. Same here, 50, 49, 48, blah, 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 until this 0. Okay, so if you want to go from this 100 to the other 100, you cannot cross this red path, because if you want to stay at the same height, you have to stay at roughly 100. Now, the key observation is in this loop tree, if you want to go from this guy to this guy, you must have to cross here one of these loops, and you have to cross at a pinch point. A pinch point in the discrete is a point in between loops. And there are very few guys like that. And it is very well plausible that none of these points has the good label 100. And if it's not the case, then your path, if you want to go from here to here, must either cross a path which has a label 50 or another orange point which does not have a label 100. And this forces for you height difference, and this is the key to prove that those 2 points will be different in the scaling limit. Okay, how much time do I have? So topology, I don't want to go into details. The topology uses the same argument, this very beautiful argument of Moore, relying on quotient of the sphere by closed equivalence relation, but I don't want to get into details. So I don't know how much time do I have, but
I think we can continue for
ask for you, what do you want to see? 5?
Yeah, sure.
Okay. So let
also questions then. So
up. So I have something to here to tell you a bit more. But if you have questions, let's start with questions maybe, or specific questions. No? Okay, so let me give you another ingredient that is key. So we have this loop tree. Oops. We have this loop tree. You see when I write here?
Yeah.
You see?
Yeah.
So we have this loop tree, and we have on every point, we have a value, z of u. And this object is really taking the Schaeffer construction to the scaling limit. And what is very important will be to look at those pinch points in a branch. So a branch is you take between two loops, between this one and this loop here, you have a branch and you look at those pinch points. So you look at the Z labels along these pinch points. And what is very important is that this guy is a 2 alpha minus 1 stable process. Why is this important? Because 2 alpha minus 1 stable process, they have a range. And imagine, for example, that alpha is small. Imagine that alpha is less than 3/2. Then this 2 alpha stable process looks like, you have got some values up, 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 up. And the range, so the range is all the values that have been taken by this process. This is a closed subset here, a closed subset of Hausdorff dimension, which is this guy. And this guy, when alpha is less than 3/2, this Hausdorff dimension is strictly less than 1. Why is that important? Because, as you know, if you take now another branch and you look at the values you see on this other branch, also you will have a closed subset of Hausdorff dimension, the same, strictly less than 1. And generically, okay, if this one says 0.9. Now, if you intersect 11 is 1 minus 0.9 inverse plus a little something. If you intersect 11 of these branches, okay, so you take this branch, this branch, this branch, this branch. If you intersect 11 of these branches, then by standard regenerative property argument, the intersection of this 11 random closed subset will be empty. Aha. And so you prove that way that if you are in the dilute phase, you cannot cross the loop tree at 11 places with the same label. Now let me give you a hint of the proof of the topology. Okay, imagine that you have a point here and you want to go to this other point here. And you ask, are they identified? Are they the same? Okay, there is a very easy answer if the process here is below. If here you are at 100, 100, and the process here, Z, is below 100, then yes, you will be linked. Almost trivial. But now imagine that the process in between takes values bigger than 100. Now, if you want to go from this 100 to 100, by the Cactus bound, you have to stay at level 100. And so that means that you have your loop tree here. And you have to find a path made of some red that has to sneak in the loop tree to stay at level 100 and to go from this point to this point. And now, kind of easy argument will tell you that if you cross, you will have to cross the loop tree at infinitely many places. And I just told you that you cannot have the same value on a branch more than 11 times. And so that's the first piece in the machine to identify the topology of your scaling limit. Okay, and maybe another, if I want to give you a teaser, another, oops, no, it's not the good one. Okay, no time for another explanation. Sorry, I thought I had another image for describing the surgery that we do along geodesics, but sorry. So I stop here and wait eagerly for your questions. Thanks.